Hello and welcome everyone to VIVA Plus 2024 user meeting. I would like to welcome everybody that is here today. This meeting is being hosted by the Auto organization and the developer team from Chalmers University of Technology, TU Graz, and University of Ljubljana, also in collaboration with OpenRadioss team. Before we begin, I would like to inform everyone that this meeting is being recorded and that the meeting will be held in different presentations, during which, if you have any questions, please put them in the chat and we will try to answer to them after each presentation. I will now hand over this meeting to Corina from TU Graz, and she will guide you through this to the schedule for today.
So also welcome from my side. It's great to see so many of you in this meeting. So what we have prepared for today is at first we will give you an introduction into the VIVA Plus models and the basic ideas behind them. And then we will show you more about the infrastructure around the models and especially the VIVA Plus validation catalog and OpenVT. Then you will hear some updates from the VIVA Plus developer team on new validations and also upcoming updates of the models for the next release of the VIVA Plus models. After a short break, we will then go more into applications of the VIVA Plus models with presentations from OpenRadioss on the VIVA Plus simulations in their open science framework. And then we will hear from Karin Brolin about the application of the VIVA Plus models for equestrian safety, and from Manuel about a comparison on average male and female response in frontal crashes. Christoph will then talk about e-scooter injury risk with focus on passenger car collisions. And unfortunately, we had to cancel the last presentation on the muscle model for injury evaluation. Matthew is unfortunately not with us today and had to cancel like last minute. Therefore, we will have more time towards the end for questions that we haven't been able to answer during the individual blocks and presentation. Matej and myself will have a look on the time to make sure that every presenter has enough time to present their interesting content. So I'm super excited about the presentations and hope you are as well. And now I would like to hand over to Johan.
Thank you, Corina. I will start by sharing my screen. So my name is Johan Iraeus, and I am working as a researcher at the Chalmers University. I'm also leading the developer group. So as soon as my computer decided to share the content, I will start. On my side, it looks like it's sharing now.
It's fine, everything's good.
Yes.
Thank you. Okay, so this will be an introduction to the VIVA Plus models, and it's mainly intended for you who have never seen or heard about these models before, but also could be good for you who have heard about the models to get a fresh update. We'll start with a short history here with the original VIVA model, because we have heard that people get confused sometimes about this VIVA, what is VIVA and what is VIVA Plus. The original VIVA model was developed by Jonas Öst and co-authors in 2017. And this model was mainly intended to be used to evaluate whiplash injury risk. So it has a really detailed model of the cervical spine. The rest of the body is also there, mainly as a boundary condition. So the rest of the body was not really for injury prediction. If we then swap to the VIVA Plus models, so when we started that, we kept the cervical spine because that was a good model, but basically throw away the rest of the model and remesh everything. So here instead, the focus is on all of the body and injury risk and all of the body. But I will show you in the coming slides that we have some special focus on some body parts also for this model. As with the VIVA, original VIVA model, we are focusing on the vulnerable female population. And one way that we do it is that the base model in our development is an average size female. All the validation, the post-processing tools, and the documentation is licensed as open source, and you will see more about that in later presentations. We have detailed skeletal models that enables tissue-based injury criteria, and I can already here mention what we mean with tissue-based injury criteria. That is basically that we look at the stress or the strain in the tissue. That is, could be a bone or something else. And we try to relate that stress or strain to injury risk, compared to something that you have in a crash test dummy, for example, where you have an accelerometer or a force transducer. So you use force or acceleration to evaluate injury risk. But on the other hand, we have simplified modeling of the soft tissue, and that is to make the models run fast. So here you can see an example where the internal organs are not modeled in detail. They are lumped together as this brown part that you can see in the picture. We have also morphed and repositioned models available to represent all road users. Of course, not all road users, but we will see soon what road users that we have models for. And then finally, much effort has been put into making the models numerically robust. And also here in the end of the presentation, we'll see some of the examples or some load cases that we use to ensure that. The model development workflow is like this. So first of all, we have used statistical shape models as the base geometry for the model. And that is slightly different compared to most other human body models, where those models are based on a scan, medical scan of a single individual. Here instead, we base it on an average geometry. So the average of many females or average of many males. As I mentioned before, we have created one base model, and this is the seated female, average female. And we do all the updates to this model. After that, we create 3 derivative models. So using mesh morphing, we create a seated male, average male, a standing average female, and a standing average male. We do validation for these models, both on component level and on full body level. And then we have requests, we have internal requests, we can get external requests maybe after an event like this. We add new validation load cases, maybe new solvers. We will see an example of that later today. And maybe issues with scale and morphing and so on. Yeah, anyway, all the updates we do is based on this average female model. And then we do the morphing again to create the derivative models. That is the workflow. Here you can see example, or here you can see the morphing. In reality, the morphing is not an animation like this. I just made it more visual. We just go from the first step to the last step in the morphing. But something that we can maybe notice here is that when we do this morphing from the female to the male, it's not just the external shape here that is controlled. Also the bones are based on statistical shape models of females and males. So when we morph from a female to a male, we also take into consideration any statistical significant differences between males and females. We have some body parts that we care more about than other body parts where we evaluate injury. One of these body parts is the rib cage. So here we have a detailed rib cage. The ribs share the same modeling strategy as the safer HPM. So you would get similar results when it comes to rib fracture risk. Not exactly the same, because we have different modeling of the internal organs and the soft tissues and so on. But they share similarities, whereas the costal cartilage and the sternum is slightly different. The ribs are modeled with the cortical part of the cortical bone in the ribs are modeled using shells. And in the middle here, you see a fringe plot. So that means that we have captured the distribution, the thickness distribution in the ribs. And this is based on an average thickness distribution of a small population. To the right, we can see the modeling of the intercostal muscles. So we have 3 solid elements through thickness. This is mainly, I would say, for contact purposes, to get the smooth outer surface and the inner surface, compared to having a shell element representing the intercostal muscles. Another area of interest is the lower extremities. Here, if we start looking on the right side, we have the model of the femur. And here we are not using shell elements for the cortical bone. Instead, we're using solid elements here. And as the cortical bone in the femur is quite thick, we can afford to have 3 solid elements over the thickness. The spongious bone here is also modeled with the solid elements, as you can see, the brown one. And something else I can mention, we are using a pure hexahedral mesh here, so we don't even have penta elements here. We have spent quite a lot of effort on doing this mesh. The upper extremities are modeled in a similar way as the lower extremities, but here the cortical bone is a bit thinner, so here we can only have 2 elements of the thickness. And obviously, I think all of you know that it's this is what is it? The time step of the model is what sets the number of elements we can have over the thickness. And the current time step of the model is, I think it's 0.4 microseconds or something like that. So it should be quite similar to what is used in the industry. One difference here is that the upper extremities, we don't really have any validation, because that was not the focus of the virtual project where most of this has been developed in. We have the reposition models, and these are repositions from any of the 4 models. So we have the base model, we have the derivative models, creating the 4 models, that's the base set, and then we create the reposition models out of those. And here we have reposition models both representing cyclists and pedestrians. And pedestrians are positioned according to TB24. To do repositioning of models, also to do positioning of the model into a vehicle environment, for example, we have metadata both for Piper and for ANSA. The metadata for Piper you can find on the OpenVT platform that we will show you where to find later. When it comes to ANSA metadata for ANSA preprocessor, then you can ask for that from your local ANSA supplier. We have, as I said, spent quite a lot of time on meshing to ensure a good mesh quality. We have a set of element criteria, and we have 100% of the elements, so all elements fulfill these criteria. And that is both for the baseline model, the 50 percentile seated, but also for the morphed models. So after the morphing to the derivative models, we spend some time fixing the element quality in those models to fulfill all the criteria. See, can go to the next slide. Can you still hear me?
Yes.
Yes.
Okay, No, it froze. Now we have so the robustness check. Here are the 4 robustness load cases we used for the occupant model. These are quite severe load cases. So if we start in the upper left corner, we have a frontal impact with an airbag. The delta velocity is 70 kilometers per hour and peak acceleration 38 g. We also have, if we go to the right then, an oblique load case where the head misses the airbag, and in some cases we get a quite severe head impact at the door side, but also the torso impacts the door side. Going down to the lower row to the left, we have a frontal impact, still a frontal seat, but this kind of mimics a rear seat. So we have removed the contact with the instrument panel and the airbag. Also this 70 kilometers per hour. And then we have a side impact with an intrusion speed of 56 kilometers per hour. And we always run these robustness load cases for every small change we do to make sure that we haven't introduced anything that makes the model unrobust. Then we also have the robustness check for the standing models. I only showed you one model in the previous slide for I think it was the females, but obviously we run it for both the female and the male model. So here we have a 40 kilometers per hour impact to a generic vehicle, but we have also pushed this model all the way up to 90 kilometers per hour impact, which is very severe. This one actually sometimes crashes, but very late around here, so very late in the sequence. Yes, that was a short introduction of the models. Here you also can see a link, and that link leads you to a documentation. So that was all for the first part, the introduction. Should we take questions directly now, or what do you say, Mate and Corina?
I think we go ahead with Jobin, and then we ask questions at the end of this block, because I currently don't see questions in the chat. Let's give people a bit more time. Thank you.
Wonderful. Then I will share my screen. Yep. Hopefully you can see my screen now.
Yes.
Yes.
Yeah, thanks. My name is Jobin, as Corina mentioned. Jobin John. I'm also from Chalmers, as you are Iraeus, and I'm part of the VIVA Plus developer team, and the team that developed the VIVA Plus models during the project virtual. I will continue from where Johan left us. The VIVA Plus documentation that he mentioned, if you were to click on the QR or the link, it will take you here on this web page, where you would find all the information you would need to know about VIVA Plus. As you mentioned, we have selected detailed models, and we have one model as a baseline. If you look here, for example, you can find more information on the modeling workflow, as Johan mentioned, and how the model is structured. This is the format we use for the identifiers we use in the model, all the property IDs, material IDs. We divide them by body regions, sagittal aspect, and the components. And the files, they are structured so that all the models, they share most of the files as a common include files in LS-Dyna. If you would go back to the home page, this is where you can download the models. If you would click that, I downloaded just before here, and this is what you would see when you download. You would have a folder called model, where you can find the 50F seated, 50F standing, and the average male seated and standing. So to show you about the file structuring, if I were to open the seated female, we would have a main file called VIVA plus 50F key, and the nodes corresponding to that. And as I mentioned, there's a comment folder which holds all the other definitions of the model, and these definitions are shared among the standing, seated, and all the other morphed models. And Johan mentioned about the pre-processing. This is where we hold the metadata for Piper and so on. And in the post-process, you would find the metadata you would need to perform calculations with dinosaur library. Coming back to the documentation, if I would click on catalog here, it would take you to the validation catalog, which is also published on Read the Docs, similar to the common documentation. And we built all our validation using Jupyter notebooks and have them openly available on OpenVT. So we'll click this link. It takes you to the repository on OpenVT, and where we keep all the validations and also the models. And here, if you would click catalog, you'd find all the load cases we have. Let's take, for example, one that Johan would be showing us again later. For example, the frontal impact, frontal experiments. And you would find the corresponding files here, handle 2011 frontal. And we've structured in such a way that the environment you would find in this folder called env, and the Dyna start files and associated files you would find under Dyna. Here we have one folder each for female and male. And if I would click the female 50F and open the main file, this is you would find the information here. You can see it refers to the environment files and all the other definitions here in the folder. And this also is made available under open source licenses. I'll come to it later on the different licenses we use for the model and the validation catalog. Similarly, the VIVA Plus models, they are also available on OpenVT. This is the view you would see if you don't sign in. I've not signed in here, and you can download all the versions, current and previous. You can see the development that's happening. And for example, if you would go to repository graph, you could see what's happening right now. As an example, you could see version 2 being developed in parallel. We would come to that also later on today. And if you would like to raise issues, or if you would like to discuss or bring things to the notice of developer group, one place you could do that is here on OpenVT. I'm trying to bring my window here where I've logged in on a different browser. And if you have an OpenVT account, and you have logged in, you would find an issues tab here where you can create issues and report things, ask questions. This is one place where most users get in touch with us. Coming back to the documentation, you would see at the end of the home page here, we mentioned open source licenses. The VIVA Plus models are made openly available under LGPL license, and all resources in validation catalog, which means the programming scripts, the notebooks, the documentation, they're all available under Creative Commons and Apache license. Now, what does that mean? What does all these different licenses mean, and what it means to you? Try to do that. I'm going to briefly show what open source means. It not only means it's free of cost, but also it means the freedom to the user, you as a user in industry or research or university. It means you can run the models as you wish in any application without any restrictions, that you can study the model without any restrictions, again, no encryption. And you're also free to make changes and update the model as you need or as you see fit for your use cases. You're also free to share with others, either the unmodified ones or the modified models. And again, share the modified version. So open source, as it means with respect to freedom, it means that you can do all these. And what does the LGPL license mean? It means you can do all of these. And when you share it with others, the LGPL license under which we have licensed the models, it tells you that you need to do it under the same license, which means you need to make the models available under LGPL license. We selected this license after extensive consultation with lawyers in the industry and universities to make sure that models stay free, or that the users have the freedom forever, as long as the models are available. And the validation setups, the programs and Jupyter notebooks, which we use for the validation catalog, they are available under Apache license version 2 and Creative Commons by, which means attribution. And that means you would need to attribute the source, that's the VIVA plus validation catalog, and there's no restriction on how you would share it again, on what license you would use to share again. And one thing to note here, I said it's a freedom to share. There's something to remember here is that you are under no obligation to share. If you make changes or if you would update the model, you're free to keep it to yourself and not share it. It's only when you share it with others, you are required to use the same license or any other license. Coming back to the documentation, we have a FAQ page because we get a lot of questions about open source on if you can use VIVA plus models with proprietary models like vehicle models in the industry. Yes, you can. There's no restriction. The LGPL license means you could use it along with the includes, and it doesn't make any difference to the environment. The vehicle models or proprietary models you use it along with, it doesn't affect the licenses of those models. It still remains proprietary. And as I mentioned, using open source doesn't mean that you need to share whatever you use it along with, or whatever you do with the model. The simulations that end up by using the models are not open source. We get questions on if you can modify the models and not share it. Yes, as I said, yes, you could do that. You can share again, maybe not under the name VIVA Plus, because that's a trademark held by OpenVT. You could rebrand and share again under a different name and so on. And something else we get to hear from the industry users is if you can send it to subcontractors to make exclusive changes for you. Yes, you have the freedom to do that under the LGPL license. And we have provided all the references to the license text here, for example, where you could go and read and convince yourself of these provisions. I would be happy to take questions now or later. This was it from my side. Over to you, Corina.
Thank you very much, Jobin. Yeah, actually, it seems we always have a bit of a shift in the questions. So I would like to start maybe with a question to Johan, as he is also now going to continue to talk about the validations later on anyway. And then we see if questions to you come up while Johan answers it. So, Johan, there was a question when you showed the pedestrian 90 kilometers per hour robustness check.
Yep.
What you actually compare that to, and if this is a validation or not, and if the model is breakable.
No. So that one is not realistic, because we don't have any failure and any element erosion in the model. And I don't think there exists any cadaver test at that speed. That would probably be unethical, because we know that the body will be very damaged at that speed. So it's only for robustness to test the model that is robust, that it can run without the error termination.
Yeah. Nico will later on talk more about the validation load cases for the pedestrian itself, but this were really only robustness checks, or?
Yes, only robustness check.
And then there is another question in the chat, if there are any differences between females and males when it comes to the ankle and foot region?
In the model, I suppose then.
Yeah.
So we have a cap. So during the morphing, we have the statistical shape models as our source and target that will guide the geometry. Particularly for the foot and the ankle, those statistical shape models are not very detailed. They are detailed for the femur and the tibia and the fibula, so the upper and lower leg, but not for the foot and the ankle, I would say. In addition, the model, the current VIVA Plus model, we have not had a focus on foot and ankle injuries, so it's simplified the model in that region. So I wouldn't recommend to use it to study that. Hope that was.
Yeah. Thank you, Johan. And if there are any follow-up questions on this, please feel free to raise your hand or just put another question in the chat. And if there are any questions to Jobin, then we can also talk about this. Someone asked why there is a wrinkle in the simulation.
Wrinkle. What simulation could that be? Need to find.
I think it was in the high-speed simulations when you have wrinkles on the skin. That's like has a waves on top.
Yeah. So I mean, that is the elastic waves propagating through the body, through the skin. I don't really know if we know how it should look like in the 90 kilometers per hour. But I mean, this model represents basically a naked person. So we have the skin, we have the soft tissue underneath it that represents a mixture of muscle and fat. And I would assume that in reality, we have these wave propagations, but usually in our models, we have too little damping. So maybe we wouldn't see this much waves or wrinkles in reality. But I don't think we have any validation data to confirm that. And also, I'm not sure how important it is. The main focus is usually to look at skeletal injuries here. That would be then the loading to the skeleton.
Thank you, Johan. And then there is another question on the upper extremity validation, but maybe we and also when the validations are done, if it's for a certain LS-Dyna version. Maybe we take those questions after we have now the validation part and start with
can
that.
do that. Yeah. So let's have a look at the validations of the model. As you're all aware of, a model is not any better than the validation status. So we have worked quite extensively on building a validation catalog. We can start here. So the current status when it comes to what has been reported in the literature and what has undergone peer review is that we have these 3 publications. We have 2 from Marcobi and 1 in Frontiers, where we could say that the Frontiers paper is the baseline validations. Here we have a lot of pendulum validations where we impact the model at different parts of the body. Then we have a specific validation of the femur or the leg, which is the one at the top here, where we also have a associated risk curve that can be used together with the model. And then in the middle, we have some specific validation that is related to rear end impacts and whiplash injury, so focus on neck and rear end impacts. I have a white corner in my lower left corner. There's a white box. Can anyone say if you can see the whole slide here?
Yeah, it's also for us here.
Yeah, something stupid in my computer. Maybe I can try to see what happens if I reshare it. Or maybe I shouldn't have touched it. So let's see if I reshare now, if it's better. I think it's better now.
Yeah, it's perfect now.
Yeah. So let's go back to this slide. So we have divided here the validation load cases in what we call component validation load cases, where we have either an isolated body part, as you can see here, for example, a femur, or at the lower, or where we exercise only a limited part of the model, as we do here with the cam tabletop that you can see in the top, where we pull a belt across the chest. We have 13 of these component validation tests. And then we have full body validation tests. We have 15 of these, where we basically exercise the whole human body model at the same time. Here we can also see some details how these validation setups are modeled. So in all cases, if we need to reposition the model, we do that during the first 300 milliseconds. We also have a critical damping at that time. And then we ramp down the damping from 300 to 350 milliseconds. And then from 350 milliseconds and forward, we apply the crash pulse. So here we have a couple of examples, one frontal impact and one side impact. So let's have a look at the validation load cases that in the final format. And this works really bad now in the presentation mode. So the Jupyter book that Jobin showed earlier, let's go in and check some of the validation load cases here. So I click this link. And then we get here. So we can see here we have some recently added. We have the gold standard that we saw an animation of in the PowerPoint, and the near side sled test, that was the other animation. So I will show you these 3 tests. If we start with this one, the gold standard 2. Typically, all the validation Jupyter notebooks have a similar structure. So we start with some basic information about who has created this Jupyter notebook and run the validation, for which version it is run for. So here you can see that it's not updated for version 1.0, even though this 0.3.2 is very close to 1.0. But it is work that needs to be done.
Johan, I would like to interrupt you because you're not sharing what you're talking about.
That is very strange because, okay.
We still see the link.
Okay, share the screen, but then I will reshare the screen. Can you see it now? Should be the web browser.
Yeah.
Okay, thank you, Matti. So yeah, this was the top part here, where we have who performed the validation and checked it, and for what version we have run it. Then we have some basic information about the experiment and the where it's documented. Also about the cadavers that has been used in the test, and anthropometric age and so on for that. Loading boundary conditions and the impact of the loading. In this case, we also have some positioning information, how they were positioned on the sled, some angles that were measured in the test, and the corresponding angles in the model. Then typically we have the first section here of the result is the model energies. So we can check that they look reasonable. So we don't have an error when we rerun it. In this case, the output data, we have the seatbelt forces. So that would be the external forces. And typically we use red colors for the 50F, the average female, and blue colors for the average male. And then correspondingly here we have the test. We have 2 tests with female cadavers and 2 tests with male cadavers. So they are also red but dashed and dotted. So then we can compare, and here we can also see in this setup, they used a higher force limiter level for the males than for the females. So it's actually a combination of 2 studies here that we are presenting together. So we have seatbelt forces, we have other boundary conditions like seat force, X force. We have knee impactors, so we have the knee forces and the feet. So after that, when we have ensured that we have reasonable representation of the boundary conditions, we can look at the kinematics. So here we have a comparison of the kinematics, the predicted kinematics, also in solid lines, with the kinematics from the tests. And here we have different levels of the spine, the head and the spine. And then in the second plot here, we have the shoulder, left and right shoulder in X, Y, and Z. And then finally, in this data set, we also had beacon markers on the chest, so we can also compare the chest compression. So the orientation of these plots corresponds to the orientation of the beacon markers. So that is the validation for this. We can go to the next one, which is a rear impact. We are not going to look at that actually. We will move here to a far side impact. Similar layout here. It's another setup. So far side, so the pulse is directed so the occupant will move in lateral to that direction or oblique, lateral oblique in that direction. And here 4 different configurations have been simulated. And those are similar to what has been reported in the literature with other human body models. We have some information about test cadavers. Again, we look at the model energies, and then we compare the signals that we have. So in this case, we have shoulder belt force, and lap belt force down here. And then we have a lot of kinetic signals compared to the test. In this case, we have gray corridors because here we only have the validation data was only run for males here, so we don't have anything to compare the female model to. Yeah, and then we have some head displacement and so on. And then we come to the second configuration. So a lot of results here. Then we can also check the near side lateral impact. Similar here, we have description of the validation load case, the loading, the positioning of the VIVA Plus models. In this case, we have less information from the test. They basically only recorded the force and deflection of the load cells. We can see that we have a number of load cells here impacting different parts of the body. And here we have two different tests. We have Wood 2014, where they run a cadaver test with females. Compare here, we can definitely see here that this part, the text should be, we need to update the text here. But here we have the greater trochanter of the pelvis, and here we have the iliacal wing of the, and we can see that they are not matching very well. The total force on the pelvis, however, matches quite well. So either the model cannot capture this distribution, or one of the plates, these impact plates, can be a bit misplaced. And then similar for the male here in another test, that's Miller 2013. And we also had a force versus time, actually, sorry, I said displacement before. Mate, you're next here.
Yes.
Sure.
In addition to all the validation cases that Johan already presented, we also have the validation for the knee joint. We did this validation based on the both 2006 and 2008 experimental data. So it simulates the impact of approximately 40 kilometers per hour. And these are the results of the simulation. So based on the kinematics, which we only have on the pictures, it looks quite similar, but also comparing the bending, the bending moment versus the valgus angle, it looks quite okay. So there is a little bit of difference if we are measuring on tibial side or on the femoral side, but the average moment that we get from the model at the validation looks quite nice and inside of the corridor that we are comparing it to. But more about the validation of individual components of the lower extremity and the pedestrian load cases, I would like to give the word to Nico from TU Graz.
Thanks. I will also share my screen. Yeah, so I would like to give a short overview of the validation of the lower extremities and some full-scale pedestrian impact validation simulations. So in basic, we can divide the method into two steps. One on the component level and one on the full scale level. I think Johan had also introduced us in this two-stage validation. In the first step, we have to model the test setup where we can apply loads to single bones or extremities. And it's important to model the full affected setup in order to account for inertias and their representation of boundary conditions. In the second step, we simulate each single test with the specific displacement time curves. In cases or in most tests, these were not equal. between the tests. And in the third step, we can compare the force time responses from the model to the experimental data and calculate our injury risk curves for the model. And on the full scale level, on the fourth step, the whole VIVA Plus models were applied, and they were scaled and positioned according to the BMHS used. Then the full scale tests were replicated. And finally, in the sixth step, the kinematics were compared and the developed injury risk graphs were applied in order to calculate the fracture risks. So we used 4 studies for the femur and the tibia, and the component validation of the femur was done using 39 tests by Iraeus, and also on the femur, the 14 drop tower tests by Iraeus by Iraeus were replicated on the proximal femur. And for the tibia, we used the tests by Harden, where a 4-point bending test was replicated. And finally, 43 3-point bending tests of the lower leg by Iraeus were replicated. And for each test, the specific force time histories of the tests were prescribed. And when we have the simulations, the time of failure was extracted from the experimental data, which allowed us to extract the strain value from the model at the same time as the failure or the failure in the experiment occurred. And these are the risk curves that we've calculated for the tibia, the femur shaft, and the proximal femur. In these diagrams, each gray point represents a single test, and the orange line shows the fitted VIVA distribution with the confidence intervals. For the pedestrian to the vehicle impacts, we used 3 BMHS studies where PARS included 1 female and 4 male with a vehicle front of a generic vehicle. Foreman conducted 3 tests with a generic sedan-shaped puck, and Snedeker had done 5 tests with a generic vehicle front. Prior to the impact simulations, the VIVA Plus models were positioned based on an equal angle approach, and some basic anthropometric scaling was applied, taking the height and weight of the BMHS into account, as it was presented by PARS in 2015. And on the full scale level, the kinematics of the VIVA Plus model were found to be in reasonable accordance with the experimental results. And I've put some examples here for the head trajectory for test number 5 by PARS. In overall, a fair correlation was obtained by the objective ISO rating score for the simulations from PARS. And I've also included a diagram of the kinematics of the head and the pelvis of the replicated tests by Foreman. And finally, I want to show an example of the application of the developed injury risk curves here for the tibia and the replicated BMHS tests by PARS and Foreman. When we apply the peak strain of the full-scale simulations of the tibia to the injury risk curve, we can simply calculate the risk of fracture of each simulation. And when we have a look at the tables, we find that in 6 of our 8 cases, we got the right fracture prediction of the tibia of in our VIVA Plus simulation when we compare the injuries to the reported injuries in the PMHS study. And I also would like to do a quick change to the VIVA Plus validation catalog. They are all singly replicated tests with fast time curves, CR fast curves, and strains in there. And finally, we get our injury risk curves. And also for the full scale validations, we have all our simulations in this catalog. So that should be all from my side. So thank you.
Thank you very much, Nico, and also Matej and Johan for this overview on the validations. We are answering some of the easier questions now in the chat, and the more difficult ones we will keep for the end of the event today, so that we can also have here some space for discussion. Now we're going to have a 5-minute break. Please continue to just write questions in the chat. As I said, even if we don't have time to answer everything in the discussion, we will answer them in the chat. So everything will be answered towards the end of today. Use that opportunity. And we will be back at 5 minutes after 3. And then we will really hear more about the application cases. So just a very quick break. I hope that's okay for everyone. Okay, then see you again in 5 minutes. Okay, so I hope everyone is back again. And sorry, I also have to apologize. Well, I forgot before that we would also still have the 2.0 on the agenda, but we decided to make a change here. So we're going to put that towards the end of the meeting. And now I would like to hand over to Paul so that he can also talk more about the VIVA Plus in OpenRadioss. We have also already had a question on that in the chat, but I think that question will be answered during Paul's presentation anyway.
Hello, yes, share my screen. Dun, dun, dun. Is that working? Not yet. Okay. Okay, can you see that now?
Yes.
Okay, great. Yeah, so I'm Paul Sharp. I work for Altair, who hopefully most of you have heard of. And I'm part of the Altair Radioss validation team, but also a contributor and part of the OpenRadioss community. I'm going to talk to you a little bit about OpenRadioss and using the VIVA Plus HBMs with OpenRadioss today. So what is OpenRadioss? Maybe some of you have already heard of it, but you can probably guess from the name that it's an open source version of the Radioss crash solver. Jobin already spoke to us a little bit about what open source means. So the VIVA Plus body models are an open source body model. OpenRadioss is an open source explicit crash code, but it's what we would call industrial grade. It's built from basically the same source code as the Altair Radioss solver, and it was launched as an open source version in September of 2022. As Jobin discussed, very similar to the VIVA Plus kind of structure. It has publicly accessible source code. You can view it, modify it, enhance it, make your own changes. And there are also pre-compiled packages available as executables that are released daily for both Windows and Linux, single precision, double precision, MPI and SMP versions. If you don't want to get involved in modifying the code, you can just download it and run it. There's an active community of members across both industry and academia institutions, and they're all committed to improving the code, creative innovation, and several research advancements and best practices are shared via the GitHub forums for the project, and we also have our own virtual and in-person user meetings. We have a steering committee of a number of members across both academic institutions and industry, and kind of industry gurus, if you like, who are guiding the development of OpenRadioss to meet the sort of latest challenges facing users in industry today when running an explicit crash code. So one aspect that even if you've heard of Radioss or OpenRadioss you may not be aware of is that it's actually capable of reading and running LS-Dyna format models as they come, so as a key file, as a .k file. And this was available even prior to the open sourcing of the code. It was a multi-year development effort that was made by Altair to enable the use of keyword format, and it was focused mainly on automotive applications, so the most commonly used materials and properties in automotive fields. Support for an awful lot of the most common Dyna input options was already mature at the time of the OpenRadioss launch, and there's been continuous further enhancement, including some contributions specifically aimed at helping what we're talking about today. A number of publicly available vehicle example models that you can find from NHTSA example. For example, like the Taurus, Neon, Yaris, Camry. You can just take those Dyna input format models and run them in OpenRadioss. Right now, no changes to the input, and we've got some examples at the OpenRadioss Confluence pages, including links to those, but also some other Dyna format like this simple tensile test that we show here. If you have access, or you do have access to the Radioss reference guide, so the Altair Radioss reference guide serves as the reference guide for OpenRadioss 2 because the solvers are basically the same. And within that, there is a list of the supported LS-Dyna keywords. So using OpenRadioss or using VIVA plus human body models with OpenRadioss, the community developers at OpenRadioss, along with the VIVA Plus development team, who you've already heard from today, worked together over the last 12 months to ensure that the next upcoming HPM release family, which is going to be the version 1.1 as it stands, should be fully compatible with OpenRadioss. And by that, I mean the Dyna input format will be compatible with running in OpenRadioss. As I've already mentioned, we've done a lot of work to support Dyna input in OpenRadioss, so that process was relatively simple. Some enhancements were made to OpenRadioss based on its behavior with the VIVA plus HBMs, adding some material and property support, making some modifications here and there. And also on the VIVA plus side, they collaborated with us to make sure that the modeling choices that were made in the next release were best suited to working with OpenRadioss. As I've mentioned, we don't necessarily support every Dyna input format, but so there was a few changes in terms of sensor and functions to ensure that the model would work cleanly with the OpenRadioss solver. So how do you do it? How do you run your VIVA plus HBM in OpenRadioss? So I've got a very short video here where I've already downloaded the VIVA Plus test suite. We've seen that in the validation tests. And here we've got the seated 50th percentile female with the Kroll, sternum, chest, hub impact. And we can see we've got the keyword format file there. So I've opened the OpenRadioss GUI, which is available from our Confluence pages. I pick the keyword file up, and then I'm running single precision here, but double precision is also available. I'm picking my number of processes, so here running in 4 processes MPI. Add the job. Okay, so this is just an existing Kroll 1971 validation test. It comes into the solver window, and we can see it says there right at the start, it's reading an LS-Dyna input format model. We get a bunch of warnings. Don't need to worry too much about those. Just talking, it's basically, you can look in the log file and it'll tell you about sort of material properties, tied interfaces, initial penetrations, that sort of thing. But so long as we pass through the model initialization phase with no errors, which we can see we've got there, 0 errors and some warnings, it then jumps into what we call the engine phase of Radioss. So that's actually running the body of the job. And I'm not going to make you sit here and wait for a number of hours while that runs, but you can see that basically it runs inside of OpenRadioss. And essentially, that's it. It's as simple as submitting your keyword file in OpenRadioss. We'd encourage you to try it for yourselves. The solver is open source and available to download from the website, and we've already seen that the occupants are available. So in summary, from the 1.1 release of the VIVA Plus models, they should be compatible with OpenRadioss. Running it is as simple as including it in your Dyna format model. You can also include them in Radioss block format, which is the Radioss native format models, in Dyna format, if that's not too confusing, via the include LS-Dyna. If you're a commercial Altair Radioss customer, you also have the capability to, in the Altair Compute Console, convert it to Radioss block format there. But now you can run full crash simulations with human body models in open source code. And just one final slide here. This was actually done by another member of the community, where Johan said the one case that had been run is this one. So Mode from the OpenRadioss community ran this and compared it with Dinosaur with the available Dyna results, and you can see that we get reasonable correspondence there with no kind of specific modifications to the model, and the dotted lines are the biofidelity corridor, and you can see that both the Dyna and Radios results are very similar in that regard. And obviously there's more validation to be done, and I think we'll continue working with the Viva Plus team to do that. So all that remains is just to thank you for your time, for watching and listening. Please feel free to ask any questions and check out OpenRadioss. Thank you very much.
Thanks a lot, Paul. And also here, if there are questions, please just put them in the chat. Paul will stay with us towards the end.
Yep.
And so far, I have seen something, just the one question, but that one you answered. We have a version. The version is running in OpenRadioss, and you have compared responses in one load case. But it's planned that we're going to compare other load cases in the future as well, or?
Yes, I think the intention is that this relationship will continue. I'd certainly be interested in basically running and comparing the entire suite of validation models with what you have for Dyna. As I say, this kind of collaboration to this point has just been to get the models running stably in OpenRadioss, and I think we're at that stage today. So with the, I don't know, maybe you can comment on when the 1.1 release will be publicly available, but that's the one that we've kind of worked towards. If you have the current release of the Viva Plus model, it's relatively easy to make that run in OpenRadioss as well, but you'd basically have to make some of the changes that are in the upcoming release yourself.
Thank you. Thanks, Paul. And I think Jobin, you will explain the.
Jobin says it's already available, so that's great. So you can go and do it this afternoon after we've finished.
Yeah, it's all on the master already. Okay,
Excellent.
Thank you, Paul. Then Karin, it's your time.
Thank you. I will try to share my screen. So can you all see my screen now? Perfect. So I will talk a little bit about equestrian safety. And this is a project funded by a Swedish insurance company called Folksam. And essentially it's part of a project where we were trying to see is the certification testing for equestrian safety vests. They can also be called body protectors or protective jackets, depending on if you're in the UK or in the US and what kind of English language you're using. But it's to prevent for torso injuries. So part of that, I used the VIVA Plus average female model to evaluate some of that. And I'll just guide you through what we've been doing. So the background question was sort of how can riders choose the safety vest with the best protection? And that's where certification come in, like we also know from the automotive industry, right? So that it's a minimum baseline of safety, and then maybe there could be additional tests so that you can distinguish between superior protection and just adequate protection. But for that to work, we need to know that the testing is representative of loading that happens in real world equestrian accidents. So that's actually the question that I was looking at here. So these are the European standard and the American standards. The Australian standard is very similar to the European. Essentially, it's a 2.5 kilo mass impacting the material of the vest. And then in the US standard, it's a 5 kilo spherical impactor instead. And in the Australian, instead of 2.5 kilos, it's a 5 kilo, but it's dropped from lower heights. So very sort of simplified testing. But then we need to know also, of course, what are the accidents causing injury. So I looked a lot into different publications, but also into accident data. And we can see that falling from the horse causes the majority of the injuries. But people are also injured when they are kicked by a horse or if they're stepped on by a horse. And sometimes people fall from the horse and then they are kicked or stepped on. So there could be a combination of these also. So the question is then if there's any correlation between the accidents that occur causing injuries and these standard testing. So if we look at the loading in a fall accident, it's determined by, of course, the riding velocity, the fall height, the size of the horse, and the size of the rider. And of course, of the material properties of the ground that you're landing on. And then the mass of essentially the torso, so the dynamic mass of the torso, which is approximately 28 kilo for an average size female. And we have impact durations of around 100 milliseconds in these kind of accidents. If we look at being stepped on by a horse, there's no study showing any data of horses stepping on people or people-like materials. So I just took data on what is the force walking in different gaits on ground. And we have a spread from 2.5 to 14 kilonewtons under each hoof. And the maximum force occurs approximately after 150 milliseconds. And for being kicked by a horse, there's a study where they had a measuring wall installed in a stable. And they measured up to 2 kilonewton forces with very short impact durations. The longest one was 50 milliseconds, but most of them were below 20 milliseconds. So I did a simulation study trying to simulate some of these loadings. I used the VIVA Plus average female model in LS-Dyna and looked at thoracic injuries by evaluating the compression, the dummy type criteria, like the compression criteria, and the viscous criterion for soft tissue injuries. But I will focus here now on using the strain in the ribs and with age-specific risk curves coming from a publication by Larsson. And this is work, yes, from Chalmers that Johan, I think, mentioned briefly in the beginning. And here's an example of the risk curves. So the ages I picked was 25, 45, and 65 years of age. And then I created a very simplified model of an equestrian safety vest. Essentially, it's an ideal safety vest because it has perfect fit. It's based on the geometry of the external surface of the VIVA model. So you could never put it on or take it off. So it's really ideal. It has a thickness of about 2.5 centimeters, which is measured from equestrian safety vest in the stores in Gothenburg. And we took material properties, estimated them from literature for the energy absorbing foam material. And then we added an external and internal surface of nylon type material. And then between the VIVA model and the vest, we have a sliding contact surface. And in the surrounding environment, we have modeled the ground, representing sort of a mid-sized gravel stiffness. And there's also a sliding contact between the vest and the ground. And I have also modeled jump rails or fences with wood material properties. So the simulations I ran were, first, I simulated both the standards. So that's the European standard, and this is the American standard. And then to get an understanding of what the European standard meant in terms of severity, I took that impactor and loaded a female torso. And then I simulated a fall to the ground from approximately 1.5 meters height in canter speed, which is about 4.5 meters per second if it's a slow canter. And then instead of landing on the ground, people typically fall off landing on fixed jump rails or fences. So here I took the two different canter speeds, the lower speed of 4.5 meters per second and a higher of 9 meters per second. And I just used the chest model, not the whole VIVA model, to save computational time. And here again is just only the chest model with the impactor from the European standard. So it's mid-sternum impact, and then an offset impact and the lateral impact. And I did not predict any fractures for any of these load cases, so it's not a really severe loading. So instead, I thought, okay, what if we increase the impactor so that it somehow represents the dynamic mass of a torso? So instead of being 35 Joule impact, it's a 350 Joule impact. And now in the mid-sternum impact, we predict no fractures for the 25 and 45-year-olds, and for 65-year-old, I predicted 0.1 rib fractures, meaning if we had 10 identical 65-year-olds, one of them would have a rib fracture. And the offset, we see more fractures, so half of the 25-year-olds would have a fracture. For 45-year-olds, they would on average have 1 rib fracture, and the 65-year-olds would on average have almost 2 rib fractures. And for the lateral impact, it's still a little bit worse loading. And then I looked at the fall accident, landing on ground with and without protection of the safety vest. And here you see the strain distribution of the rib cage, and it's very low strain. So I did not predict fractures here either. And it's quite a low friction coefficient between the rider and the vest and the ground. So maybe not very realistic. But we see that the safety vest is doing a good job. It reduced the chest compression by 40% almost. And here we have the torso impacts for the fixed jump rails or fences. So the two left ones are different canter speeds, 45 and 9, and without the safety vest. The two to the right are with the safety vest. So here it's just inertial loading from the speed of the torso going into the jump rail. And here we see for the lower speed, we predicted no rib fractures, but for the 9 meters per second canter speed, we predicted rib fractures for all the different ages. And with the safety vest, that rib fracture risk decreased a lot. So for the 25-year-olds, from on average almost 4 rib fractures to 1. So then the question is, the certification testing, the loading, which was the aim here, is it comparable to the accidents that we simulated in terms of loading of the riding vest? So the duration of the impact for the testing, standard certification testing, it's about a 15 millisecond long force curve in time. For the fall, in this case, 74 milliseconds. For the jump rails, the lower speed 90 milliseconds, and the higher speed is a 60 millisecond duration impact. So we can see here that the certification testing is not really representative of these fall accidents that I simulated. And if we look at the maximum compression of the vest itself, for the certification testing, the European was a 60% maximum compression. The US was 82%. In the fall accident landing on ground, we only had 38% compression, so much less. The 9 meters per second impact on the rail was the one that was closest in 85% compression. So then the question is, it's a sort of the summary then, that we most of the injuries, the torso injuries are in equestrian accidents are caused by fall accidents. And if I look at the European standard and apply it to female torso, it does not cause rib fracture. So I don't think it really does any correlation or predicts any knowledge about for that testing if that is a good vest to protect from rib fractures or not. The impact duration of 15 milliseconds in that testing, it's representative of hoof kicks, but it's much faster than the impact duration of 100 that's representative of the fall accidents. And the impactor mass of 2.5 kilo is about 1/10 of the torso dynamic mass. So then the question was that the certification testing, is it representative of loading in real world equestrian accidents? And our answer is no, it is not. So we are now working on a continued project where we are using or will be using the VIVA Plus model to come up with good novel certification testing that could be more representatives in terms of loading of the vest in accidents. So shortly then, what my VIVA Plus user experience was. It was numerically robust for all the load cases that I simulated. A big plus for the strain-based rib fracture risk that it was really useful for me, and one of the major reasons for that I chose this model for the simulations. For some, as I mentioned, for some of the load cases, I only used the torso model. And that created a little bit of headache or maybe manual work to get the model running. It was not very easy to just remove parts, and then I got some numerical instabilities until I fixed it. And it was not possible to run the post-processing scripts straight on to get the rib strain predictions that are supplied on the VIVA Plus web pages. So I had to do my own scripting for post-processing. But I will definitely use the VIVA Plus again, and I'm open to any questions.
Thank you very much, Karin. I think we considering the time, we would also do it as previously. People just put the questions in the chat, and what you can answer in the chat, you answer directly, and the rest we keep for for afterwards. But thanks a lot.
That sounds perfect. Thank you.
Okay, then I think it's time for Manuel to tell us a bit more about occupant simulations. And Dilip, I did see that you were raising your hand. Maybe you can put the question in the chat or bring it up afterwards.
Can you see my screen?
Yes, it's working perfectly.
Perfect. A second. There. Okay. Hi everyone, my name is Manuel Valdano and I work at the Universidad Pontificia Comillas. I would like to start by thanking you for having me and the Foundation Linea Directa, which funded this study. So, there. So, previous studies have focused on using crash databases with logistic regression models to study different factors in these crashes, which lead to injuries. They have observed that men and women don't have the same injury risk in the same crash conditions. Usually women have a higher injury risk than men. So we wanted to focus on this in the source of these differences and use a finite element model to study them. We thought that the VIVA Plus model was a perfect model for this use case, for this study, as this model allows us to represent both 50 percentile female and 50 percentile male in these simulations. We focus on frontal crashes. For this reason, we use the generic vehicle interior from Iraeus and Lindquist, and we duplicated interior so that we can also simulate passengers in the front seat. The test matrix for this study was that we use both 50 percentile male and female in the driver and passenger position, and we simulated crashes at 30 frontal crashes at 30 and 65 kilometers per hour. Using the Dinosaur library, we obtained the outputs of the simulations. For the sake of time, I will just focus on the probability of sustaining an ACE3 plus injury from HIC 15, an ACE4 plus injury from damage, and the expected number of fracture ribs. Here you can see a video from the crash at 65 kilometers per hour. In the left-hand side of the slide, the female model in the passenger position, the male model in the driver position, and the right-hand side of the slide, the male model in the passenger position and the female model in the driver position. Okay. Going to the results of the simulations, I will just focus again in the 65 kilometers per hour simulation. In the left-hand side of the slide, you can see the probability of sustaining an ACE3 plus injury from HIC. You can see the position for both driver and passengers and the occupants analyzed in this table. So as you can see, passengers are more susceptible to have this kind of injuries. And you can see that for drivers, female have a larger risk of sustaining these injuries, and for passengers, the male ones. When you go to the damage, you can see a similar trend, but in this case, the female driver occupant have a larger risk of sustaining an injury from damage. With analyzing the video from this crash, you can see in the bottom right-hand side of the slide, there is a sudden rotation of the head after impacting against the airbag, which rotation resulting in this larger risk, because this rotation was not observed in the other simulations. And lastly, for the expected number of fracture ribs, we calculated this number for a 25, 50, and 75-year-old occupant. As you can see, this number increases, and as the age also increases. And in this case, again, passengers were more susceptible to have these kind of injuries than drivers, and male occupants were more susceptible to these injuries than female occupants. As you can see, the results differ from those observed in the databases. So we are focusing on, we are continuing this study and focusing on more anthropometries. So thank you very much for your attention, and I will be happy to answer your questions.
Thank you very much, Manuel, for this interesting presentation and analysis. I'm sure that we also have questions for you, so we just wait to collect all of them and hand directly over to Christoph.
Yeah, hello also from my side. Today I would like to give you a short overview on our study we have conducted on e-scooter injuries. So why we have conducted the study, as we see more and more e-scooter riders and also increasing number in injuries, we have asked ourselves how we can assess the injury risk in e-scooter accidents and how we can derive recommendations for accident and injury prevention, especially in case of passenger car collisions, collisions with pedestrians, and also in single accidents of the e-scooter riders. To answer these research questions, we have used the following method. So first of all, we have conducted volunteer tests, and these volunteer tests we have split it into two different tasks. So one task was that the volunteers were driving along a predefined road where we have a traffic observation system, and this traffic observation was used to get driving velocities of the e-scooter riders. And then we also have asked the e-scooter riders to drive in our laboratory, where we have a motion capturing system. And this motion capturing system was then used to get the driving posture for the e-scooter riders. And this we have done for females and male volunteers. And with this data we have collected in the volunteer test, that's then our input data for the simulations with the VIVA Plus human body models. Just one slide to the results of the volunteer test. I have here an example of a driving posture where you can see that the right foot is in front and the left foot is a little bit behind. And this is then our target posture for the human body model simulations. I don't want to go too much into detail on that. So if you're interested in the results of our volunteer study, please have a look on the publication of last year's ICOVI. There you will find all the details on the volunteer test. For the human body model simulations, to conduct them, first of all, we had to position our models. So starting from the base models, the VIVA Plus 50F and 50M standing models, and the target position of our volunteer test, we have positioned them using the Piper positioning tool and have positioned them on the e-scooter models. These models are not yet on the OpenVT platform, but we will put them on there. So you will also find then the e-scooter models as well as the positioned VIVA Plus models. So you can use them then for your own simulations. And that's how the simulations then look like. So just an example of passenger car collisions. You can see the generic vehicles we have used and the VIVA 50M on the left and the 50F model on the right side. Then we have, from these simulations, we have analyzed then the injury risk for proximal femur fractures, for tibia shaft fractures and tibia shaft fractures. And as you have heard before, for these body regions, we have the injury risk special for the VIVA Plus models. We also have analyzed the fracture risk of the ribs, the brain injury risk, and the skull fracture risk. I just want to give you or present some examples of the results based on the brain injury risk and the skull injury risk. If we have a look on this graph, you see the injury risk for two different vehicle velocities with an e-scooter velocity of 25 kilometers per hour. And you see if we lower the collision speed from 40 to 26 kilometers per hour for both the 50F and also the 50M, we are able to reduce the brain injury risk in case of a passenger car collision. This is also the case for skull fractures. Also here, if we are lowering the collision velocity, we are able to reduce the injury risk. We have also analyzed how we can reduce the injury risk if we are using a helmet, and this you can see here. So for a 40 kilometers per hour collision with a passenger car, so on the left, you see if no helmet is used, we have quite a high injury risk, and on the right, if a helmet is used. And a closer look on the 50M, plotted in blue, you can see that through the helmet, we are able to reduce the injury risk, but we are not able to reduce the injury risk for the 50F. We had a closer look on the simulations, and if we have a look on kinematics, we can see that the impact on the bonnet for the 50M, the average male, the head, or first the helmet is impacting the bonnet, and if we have a look on the average female, a little bit different in the kinematics, and there we see that not the helmet is impacting the bonnet, but the face. This corresponds also with accident data we see. If we have a look on accident data of e-scooter accidents, then we see that especially we see a lot of fractures to the face area. So that's something that should be investigated further in the future. Summing up this study, so we have seen that severe head injuries were observed for all kinds of accidents, so for vehicle collisions, the single accidents, and also when an e-scooter is colliding with a pedestrian. We have seen that the velocity or collision velocity of the passenger car has a bigger influence than the e-scooter velocity. When we have a look on collisions between e-scooter riders and pedestrians, we see that also the pedestrian suffers severe head injuries. What we have also seen that if we are reducing the e-scooter velocity, we also can reduce the injury severity in case of single accidents and also of the pedestrian. And when our helmets can reduce the head injury risk up to 44%, depending, as shown before, on the kinematics and if the first impact takes place on the helmet or in the facial area. Yeah, this study has got funding from the provincial government in Styria, and this brings me to the end of the talk. I'm happy to answer your questions.
Thank you very much, Christoph. I think yes. Currently, we have one question in the chat for Karin. So maybe Karin, you can have a look. Otherwise, we answer it later on. I would now bring up also a teaser towards VIVA Plus 2.0. As we've seen in Christoph's presentation, he only used kinematic head injury risks, head injury criteria, and we also have another question in the chat on lumbar spine improvements. I think it's a good time to show what's coming up next. Johan.
Yes. So, tell me when you see the presentation. Maybe now?
Fine, we can see it.
Yeah. So this will be a presentation about the about the upcoming updates for version 2.0. First out is the pelvis model. We have updated the pelvis model. The geometry is the same. The mesh is the same, but we have added distribution of the cortical thickness. So the shells now have nodal thickness, which at least makes it possible in the future to look at the tissue-based injury criteria. We have some validation for the pelvis, but I would say that we need some more work before we have the injury risk function here that we can use together with this model. We have calibrated some properties here. So we have basically two joints in the pelvis. We have the pubic symphysis and we have the sacroiliac joint. Pubic symphysis is the joint in the front of the pelvis. And here we have made a choice to only use solid element representation here. In reality, we have a bunch of ligaments as well, but we have used solid representation and calibrated the material properties to fit to experimental results. So we can see to the left here that we are matching the stiffness in tension compression for the female quite good, whereas for the male not as good. So we have not modified the material properties. We just use geometric or morphing between the males and the females. So this is an indication that maybe something more is needed here to capture both the female and male response. We have also calibrated the sacroiliac joint, and here we have some more loading conditions. So in the top graph to the right, you can see displacement in a bunch of different directions: superior, inferior, anterior, posterior, and medial. And generally, we are within the range from the experiments. In the bottom, you can see the rotation. So here we have bending. So we have flexion, extension, lateral bending, and torsion. And generally here, the model is a bit on the compliant side. We don't have good data here representing the difference between males and females. It's in the Miller experiments. I don't recall if it's only males or if it's aggregated data, but we don't have that level of detail in the experiments. So this is more a comparison between the male and the female model than evaluate and comparison to experimental results. The validation we have is that we have recreated tests from GIMO. So we have two quasi-static load cases that you can see to the left. One loading to the iliac wing to the top, and one loading through the acetabulum with the metal sphere. And these are basically within the corridor. Then we have some other tests, dynamic tests in the same study. In the publication, there is a limited amount of data, so we only basically have an upper and lower corridor. Our model, as has been asked in the chat, does not include fracture or an element erosion. And actually, in most of the cases in the GIMO test, the pelvis fracture, it was actually only two tests, one male and one female, where it didn't fracture. So when we compare the results to that, we need to remember that in reality it's fractured in most of the cases, and of course that will change the kinematics and kinetics a lot. Next, we have an updated lumbar spine model. This model was presented last year at RCOBI. And the same model has been implemented in the VR Plus models and the safer AHBM models. So it's the same mesh and the same material properties and so on. And also here we have created a pure hexahedral mesh for the spongious bone. The cortical bone is modeled with shell elements. We have implemented nodal thickness of the cortical bone that you can see in the lower right corner. So typically, the thickness of the cortical bone in vertebra is quite small. We have anisotropic material in the trabecular bone because in reality, the trabecular bone is much stronger in the inferior superior direction, the main lobe direction, compared to the other directions. That is also included. And we have a risk curve, associated risk curve, that is based on the strain in that inferior superior direction. We have tuned the ligaments. Actually, the ligaments are based on tests, physical tests, but we have to tune the initial length of the ligaments. So using these two studies, we could tune in initial lengths, and we have included a parameter in the model called lumb flex. And we have some recommendations how to set this lumb flex. So we set it to 0 or -1, depending on if it's a standing model or a seated model. And that represents the initial slack that we think is also that you have in the human body model, or the actual human body as well. Validation, we have two validation data sources, one from Yamamoto. Here we have flexion extension, lateral bending, actual rotation of the whole lumbar spine. In the paper, you can also find information of each of the FSU segments. So for example, between L1, L2, L2, L3, and so on. Distribution. And then we have another validation load set from the Metropolis, where we have also some information about compression tension and posterior anterior shear in the model. And as you can see here, for example, we have set this lumb flex parameter to -0.5, which represents something in between the standing posture and the seated posture that we think is representative of the curvature from the physical test here. Yes, over to Jobin or Yash. Should I continue to click through the slides? Then you can talk.
Yes, I think you can do that. Yash must be trying to unmute himself. We don't hear you, Yash. I can see that he's unmuted, but he is not audible. I think I can take this. This is the development of the head that we have been working with last couple of years. And here the focus has been to predict the fracture on the skull, skeletal fracture on the heart tissue specifically. So here again, we have a detailed mesh on the head, the cranium, and the frontal bones. We have a node-wise cortical distribution across the interior and outside inside of the cortical table. Also, we have a solid representation of the brain. And this is primarily right now for mass representation and to get the right boundary conditions. But the brain mesh has been developed, keeping in mind the details and sections of the brain for further development in future. And here are the calibration tests for the cortical bone and the trabecular bone. I think in the interest of time, I can move on to the next slides and show you the validation test also, where we performed lateral impacts on the forehead, temporal impacts and the frontal impacts, and also a vertex impact with the mass dropping on the top of the head. We have a couple of slides showing some selected responses. We are preparing this for publication, so this is going to come out soon, and you'll see a preprint out soon. And this is the lateral impact, Raymond et al. Blunt impact. And you can see the response of the female model, the average female model here in low speed, 20 meters per second and 35 meters per second. And next is lateral impact with the drop, and this is only the skull without the soft tissues. Again, 3 different velocities, ranging from 3.5 to 6 meters per second. Yep, more details would come soon in the publication that we are preparing. And with that, I would end here. And these are the big updates coming in the version 2.0.0. Watch out for release later in the summer. I can close updates from the developer team by sharing a little bit more about the VIVA Plus community. And as you see here, we have a community where people contribute at different levels. We have users, like most of you today here, who are basic users of the model. They come from industry and university. And some of these users contribute back by reporting issues, performing model validation, or adding to our documentation. And again, some of these contributors, they again contribute to the development itself by fixing issues and implementing new features. Right now, we have about, I could count 9 off the top of my head, 9 developers. And we also have a steering group not necessarily associated in any way with Viva Plus, but coming from industry and academia, who help us prepare the model roadmap. And we are 4 maintainers who are maintaining this on a regular basis with bug fixes and stability issues and so on. So if you would like to join, you're welcome. We are an open community. We keep in touch in different ways. You can use the issue board, as I showed before. We use the lib community, though we are not quite active there now, but we respond to questions there. You could also send us an email at vivaplus@ofto.org. You'll find the email address and all the details I mentioned on the Viva Plus documentation homepage. That's it from us today, and we will go on to answering some of the unanswered questions that we have had in the chat. Thank you.
Thank you, Jobin, very much. I think most of the questions are answered, in fact, in the chat. One thing that has been asked is about the VPS model of the Viva Plus, and there I would like to give Thomas the opportunity to comment on that, if he's still here. Okay, maybe we...
Sorry, Karina, Thomas is not here.
Okay, so we lost him. Then you can say something about it, Preeti, sorry.
Sorry. So I'm Preeti Yadav from VIVA GmbH, and I'm working on the conversion of the Viva Plus model in PAM-Crash. The status of the model is we have done the geometry and constraint transfer for material is still ongoing, and with all the validation, and we are expecting to finish this work by April or May sometime.
Thanks a lot. So this is also an exciting development that is currently ongoing. So question to Johan, Jobin, Christoph, Karin and Manuel, is there anything you would like to add on to the questions that you have answered in the chat?
No, I think I've answered most of the questions. So if you have time, look into the chat and put the questions and the responses. That will give you some additional information. There is, I think, just some unanswered question about the brain right now. But otherwise,
Jobin is on it, I think.
Yep.
I'm on it. Yash was the one who ran that, and so I should get back to him, but off the top of my head, the brain was not there. It was just the cranium.
So then maybe it's time to say goodbye. Thanks a lot for everyone who presented, really nice presentations, and thanks for everyone who participated. Jobin, especially thanks to you. You did most of this organization work and found the presenters for this talk.
Yep, thanks to all presenters. It was wonderful to hear all of you.
Yeah,
looking forward to an exciting year.
Yeah.
Yep. Thank you, everyone.
Thank you.
Thanks for today.
Bye-bye. And hopefully we will have another user meeting like that upcoming year.
Yes, it is planned.
Yes.
Depending on user interest, of course.
Cool. Then Preeti can show the VPS model, and we can see more OpenRadioss results there for additional validations, and more of the 2.0, or maybe then even as 3.0. Who knows?
Yeah. Fingers crossed.
Cool. Bye-bye.
Bye-bye.
Thank you.
Bye.